All right, well, it's a few minutes past our start time. So let me go ahead and get us going here, get us started, and of course, remind you of the big picture here. Don't lose focus on that as we get started with our E&M this semester, and so far it's been only the E part, the electricity part here. And so the goal here is to get through chapter 24 this week. We probably will at least get through all the ideas of chapter 4 and start getting into some examples. But I know I won't get as many examples as I'd like to do. I never do. But same as last time, when we get to the weekend, I'll have to rethink about this. And like I did this Tuesday, when we come back, I'll have to say, okay, should I do more examples? And this Tuesday I did, and I was glad I did, at least after hearing a lot of comments that said, okay, I'm glad you did a few more. And because I did a few more, we're a little slow getting started on chapter 24, so we might pay that consequence now, but it again probably will be worth it. All that is to say is here's the big picture. I was trying to convey to you Gauss's law, that working with flux is another convenient way of finding the total electric field. So our first chapter, chapter 23, we did this, Coulomb's law. We said, what is the electric field from a single point? And we know that you can add up all the points, and even if it is a curved object or a loop, or we did a loop or ring, we did a disc, and we did a bunch of different examples, and we added them up to get the total field. From that gave us the force, from that gave us the acceleration, velocity, and position. And at least a lot of questions I had yesterday was that one that the proton went up and arced over and had a land, and so obviously it involved a lot of mechanics. And it said, well, what angle do you have to shoot the proton in order to hit that particular topic? So most of the questions I got were questions about the mechanics, not so much about the E&M. And maybe that's good in the sense that the E&M is getting across. I suppose it's bad in the sense that maybe you've forgotten your mechanics, but it's a good review nonetheless. What I want to get across today is that using this concept of flux will allow us a second alternative way of getting to the total electric field. And so that's what I want to show you. And we left off with this picture. In fact, maybe I should back up a picture. Let's go back to that egg shape here, just again to have that mental picture here of what is flux. And so I'll say it again and hopefully get the picture across more and more today. And as you do the reading, flux is really how many electric field lines go through a surface, okay? And so this is our surface, and the ones over here are going in, the ones over here are going out. I'll ask it again, what is the total flux through this ellipsoid of revolution? 0. Why 0? Yeah, and we got the answer by a visual picture, right? We looked at the electric field lines. We see that the ones going in exactly match the ones going out. And the ones going in, as we said earlier, would have what sign? Negative if they go in, right? If they come out, what sign? It's positive, because how do we calculate a little bit of flux? I'll call it d phi sub e. A little bit of flux going through this little surface, surface number 3. What did flux depend on? Well, the strength of the electric field, so remember we're representing the electric field by how concentrating these lines are in the picture. What else do we need? Yeah, the angle, I heard somebody say. Good, cosine of the angle. What else do we need? Yeah, the area. And so looking at this, and of course I'm writing it in differential form here with my calculus, but there's the electric field, there's the angle, and there's a small amount of area. And so to get the total flux going through a surface, we would have to add up all the fluxes. All these little squares or rectangles would have to be added together, and then we would get the total flux. And since it depends on the angle, we might as well treat it like a dot product and write it in this form. And that obnoxious ding is going to drive you and me crazy until I turn off my phone. There we go. All right. Now, and that's where we left off. There is our flux. So, here's what I want to do. I want to start doing my first example of calculating flux. Haven't really got to Gauss's law yet, but we mentioned this one in passing. It's probably the easiest one to do because we already know the answer, and the idea is to look at the technique. Let's start here. What is the total flux through this cube? Yeah, it's 0. And just to remind you of Tuesday, this over here is representing the electric field. They're trying to say the electric field only points in the x direction, and it doesn't increase or decrease. It's a uniform electric field. Because if it was changing in its size, right, the lines there would not be parallel. But by being parallel, they have the same concentration. And so they're trying to say the electric field all the way through here is the same amount. Okay, and of course I'm just looking at the picture. If you read the book, they say, and then they do the example, a uniform electric field pointing in the x direction. But what I'm trying to say here is I could then find the flux, say on surface number 1. I could also find the flux on, say, surface number 2, surface number 3, surface number 4, surface number 5, and surface number 6. And so let's look at each of these separately, as we, again, did real quickly at the end. Number 1, they're labeling here on this far side, the YZ plane here. And if you write this out as E dot dA, hopefully the first step you will do is to write out the dot product, cosine of the angle between them. And so I will start there. What is the angle then between the electric field and the area? Okay, good. And then hopefully they're showing it here, but as we said, and it's worth saying it again, if you have a surface, so if this desk up here represents this cube, and this face number 1 is representing this side over here, so here's face number 1, with the electric field going into it, we said that the direction of the area vector is perpendicular to the surface, pointing outward. And so using my right hand as kind of an indication, I'll just hold it against this surface here, right? It's pointing that way. It's pointing in what you might call the negative x-axis. And so that's what this picture is. So the electric field points in the positive x-axis. The area vector points on the negative x-axis. And as I heard more than one of you say, that angle would be 180 degrees or pi radians. And what is the cosine of 180 degrees? -1. So how about if I write this as negative E dA? Now again, just showing you our quick calculation, that's the first one, is focus on the dot product. But in addition to that, let's focus on the electric field. What else do we know? Well, we were told the electric field is a constant. This little integral says what? Well, it says add up the value of the flux, the electric field, over that whole surface number 1. Well, what's nice about this problem is, what do we know about the value of the electric field over this whole surface? Yeah, it's a constant, right? It does not change, which is really nice because that means we can pull out anything that is a constant. All right? And now I'm left with a very simple integral of dA. What's that? That's just the area of surface number 1. And how do I get the area of a square? Yeah, it's just L squared. So this final step, and I'm kind of out of room here, but there would be my first example of a very simple calculation. How do I get the flux on surface number 1? Well, let's move to surface number 2. I would start with the same idea. What is the definition of flux? It's this. I would take the dot product. That would be EdA cosine of. And instead of having 2 steps here, what is this? Well, let's jump to surface 2. Surface 2 is this one. On this bench here, it would be this side. And where the direction is dA. Positive x-axis, right? And the electric field is still in the positive x. So what's the angle? 0. So this should be cosine of 0. And of course, what is cosine of 0? 1. And like we did up here, what could you say about the electric field? It's constant. So I'm going to pull out the electric field, and then I just get an integral of dA, and so then I get E times L squared. But I get a positive number. So again, notice that on one surface where the flux is coming out, it's positive number. On the other surface where the flux is going in, it's negative. And the fact that they come out to be the same, hopefully, is not a surprise to you. You already told me that it kind of looks like what goes in, what comes out. The other 4 surfaces are probably the easiest of the calculations, but let's look at them. Look at surface number 3. I would encourage you first to maybe look at the dot product. And in this picture here, it looks like surface number 3, being this top one, coming over to this desk would represent this top one. Maybe my right hand being the direction, it would be pointing up, right? Which way is the electric field? Well, it's still the x-axis. So what's the angle between them? 90. And it's 90 everywhere over that surface, right? And so I can put in 90 degrees and actually pull it out in front of the integral because it's 90 degrees everywhere over the surface. And of course, what is cosine of 90 degrees? 0. So the total flux through surface 3 is 0. And again, hopefully that fits your mental picture, right? That's the whole idea. Nothing's going in or out of that surface. That one's just skimming across the top. What about the bottom surface, number 4? How much flux do I get there? I get 0 there. Why? 90 degrees also, right? Same basic idea. This is the bottom one here, and it's skimming across. How about this front surface, which they don't label as 5, or the back one, which, again, they don't label as 6, but that's what I mean by 5 and 6. What would be the flux here? And so I didn't hear anybody say 0, but maybe because that's so obvious, right? So all those are 0. And if I were to take this one step further and say then, what is the total flux through this cube? I would add up all 6 faces. And what am I going to get? 0. And so if I say flux, and I'll just put total, is going to get 0. And I thought this would be a good lesson of saying, okay, let's do the calculation. Let's look at each individual surface. And you can see I've got negative numbers, I've got positive numbers, I've got 0. And when I add them all together, I come up with 0. And that's kind of what I expected. Yeah.
So, just a silly question, actually. Since we used the angle for the first area as 180 because we just used the angle between the direction of the
right
and the area, it makes actually no difference to use it for a floor, which would be an angle of cosine 240, 270.
Oh, fair.
Is it safe always to say 90? It doesn't matter.
Yeah, I go to the angle that is less than 180 degrees. That really goes back to chapter 7 and our idea of a dot product. Okay, when we did the dot product, we were saying once you take the dot product, this is the magnitude of that vector. So don't worry about whether the electric field's pointing in a positive or a negative direction. This is the magnitude of it. So this only will be a positive number. And that's not quite what you were asking, but I do want to point that out, that this is the definition of a dot product. Okay, that's the magnitude. So that's only a positive number. This is the magnitude. This is only a positive number. And then this is cosine of the angle. And again, going back to our definition of the dot product, that's really your question. It is the angle that is less than 180 degrees. Because when you have two vectors like this, you go to take the dot product. Do you use this angle? And it's this first one that we've used. And so continue to use it. So don't use 270 here. I think that tells me you're missing the definition of the dot product. Would it work in this case? Yes. And I think it might work in all cases, but careful.
Yeah, but you have to just know the direction.
Yeah.
If it is that big, it might be negative.
But I do want to emphasize this. It is not 270 because of the direction of the area vector on a standard grid that you measure 0 at x-axis and then go around. And I fear that that's what you're doing. This dot product means the angle between those two vectors. It does not mean the angle as measured on a standard rotation on a grid system. Okay? So again, if you put the 270 in there, you might be missing something important here. It just happens to be the same this time because the electric field is pointing along the x-axis, which is our standard way of measuring angles. Okay, but that angle is not the angle from a standard measurement. That angle is the angle between those two vectors.
When doing these angles, if you're going to go clockwise instead of counterclockwise, can you just use negative angles, and will that preserve the idea of the box and not just a coordinate system? Is it the same answer?
Yes, it is. Yes. But again, I think it is much simpler to just look at that picture and say, it is the angle. Don't worry about plus or minus, clockwise or counterclockwise. It's the angle between those two vectors, and it's the smaller one, not the one greater than 180 degrees. Yeah. Okay, well, keeping that in mind, let me ask you this. I've shown you a couple of cases already of the flux. There was the egg before this. Now there was the cube. The flux was 0 in both those cases. And we finally get to where we're going. Gauss's law. Gauss noticed the same thing. Would there ever be a time where the flux is not 0? Right. And this was Gauss's brilliance, and you guys are just as smart, obviously. Right? You are realizing that the only way the flux, and maybe I'll do this one first, would not be 0 if you had a completely enclosed surface is if there was some charge inside. This picture shows a positive charge inside and saying that here is an example of flux coming only out, not in. Now, we could have something more complicated, but the key here, if I jump to another picture, is that if you have the charge outside of your surface, like this, and you have a completely enclosed surface, whether it be the egg I showed you earlier, or whether it be the cube, or whether it be this crazy shape, what would you say the flux is through this crazy shape? Again, 0. Why? Visually, I'm hoping you see what flux goes in equals what flux comes out. Whether the area that it goes in is equal to the area it goes out doesn't really matter. And in this case, it does not. Here we can kind of see on this part of the object, the flux is going in. So we're going to get negative values there. The other places from here around, we get positive values. And where we get positive values, we have much more surface area, don't we? But we also have a weaker field, don't we? You can see that in the concentration of those pictures. The lines have spread out. So by the time the field comes out of our object, we have more area, but less field strength. And that's why we get the same amount of flux coming out as going in. And so the total flux of this is 0. And so you're seeing a very important point that Gauss saw, that the only way you are going to get a non-zero number is if there is some charge inside of that surface. Here is a picture that they don't even show you the lines of flux, but they do say you have some charges. You have 1, 2, 3, and 4 charges. And if you look at this surface, say this first surface S, would there be a non-zero or zero flux for that one? Yeah, it would be non-zero because we have something inside of it, right? If we jump over to what your author calls surface double prime, there's no charges in here. What would be the flux to this one? 0. Now, it could be a very complicated picture because you would have flux coming from this one, you would have flux coming from this one, you would have flux coming from this one, or flux going into this one if it's negative, flux going into this one if it's negative, flux going into that. Oh, and that one too. And so the amount of flux and the direction of it get very, very complicated here. But here's what I want you to see. This leads to Gauss's law, and that is really the whole chapter. What is Gauss's law? How are you going to use it to solve problems? And Gauss realized that there would be a non-zero flux on a closed surface if and only if there were charges inside. And so no matter how complicated the electric field looks, the flux here is 0. Same that goes in is equal to what comes out. Because we can only start new flux where there are positive charges, and we can only terminate flux where there are negative charges. And so there would not be any increase or decrease in flux from that surface. But there would be for that one, and there would be for that one. And so Gauss realized that using flux is going to be a convenient way of figuring out the electric field. Here's what I mean by that. Let me write down in equation form what we just said. We said that if you take the flux and you take a surface that is closed, here's a symbol that you may not be familiar with. And so I want to point this out because so far I've just been teaching you what is flux in general. But Gauss's law is not just any surface. Gauss's law is going to be only applied to closed surfaces. So you'll see why I had that egg shape, it was closed. You can see why I had the cube. When you did all 6 sides, it was closed. This is a sphere, and the ones I had before it were kind of weird shape and objects, but again, closed. Okay? If you calculate the flux on a surface that is completely closed, again, whether it be an ellipsoid of revolution, whether it be a cube, whether it be a sphere, if it's closed, the flux will come out to be 0 unless there's a charge inside. And if there's positive charges, then the flux should be coming out. So we should get positive flux. If it was negative charges inside, we should get negative flux. And so here is what Gauss realized, that there is a direct connection to the flux, which is connected to the electric field, so this might be a nice way to calculate the electric field, and the charge is enclosed. And what's nice about that, it's only the charge is enclosed. What if you have other charges around? You don't need them in your calculation. Now, do they contribute to the electric field? Yes. But you don't need them in your calculation. And that may make what looked like a hard problem an easy problem, because you only have to deal with the ones that are inside. But I point out that it could lead to some confusion, and I've had students say that. They said, well, don't the charges on the outside contribute to the electric field? Yes, they do. And if you had done it by Coulomb's law, you would add up all the charges. But when you do it by Gauss's law, even though the outside ones contribute, you don't have to worry about them in your calculation. And that's the beauty of it. And so this second method will be an alternative way to go, and sometimes this method will be much easier and much simpler to do than Coulomb's law. And I'll show you some examples in a few minutes. Other times, I got to admit, Coulomb's law would be much easier and much simple. So that's why we are learning 2 and eventually 3 different techniques to get the electric field. Now, I put a question mark up here because, again, Gauss says this must be your logic, that the amount of flux through a closed surface has got to be proportional to the amount of charge that is inside. And so, what's the proportionality constant? What goes in front? Is it nothing, like the number 1? Is it 7? Is it Coulomb's constant? Kind of would suspect there might be a Coulomb's constant in there somewhere. But we can give it a try. And so here's how we're going to come up with Gauss's law. Let's do our first one. Let's do probably the easiest flux calculation with a charge on the inside. I mean, I just did the cube, but it had no charges on the inside. But let's do a flux calculation with just a point charge, because we already know the electric field from the last chapter. And so we can do this. So here's what Gauss has said. In order to find this, all I got to do is take a charge. So there's my charge. So he puts a positive Q on the inside. He already knows that there would be an electric field pointing outward, and let's put a surface around it. Now I want to emphasize, this is a mathematical surface. He's not literally putting aluminum foil around the outside of something, okay? There's not a material here. This is a mathematical surface. Pick any surface you want. You will get the same flux coming out. Watch, let me back off of this picture for just a second. If we go back to the picture that I had earlier, this one, look at the flux coming out of surface number 1. And compare that to the flux of surface number 2. How do they compare? Yeah, they're exactly the same. Just looking at the surfaces, which one do you think you would rather calculate? One with a lot of symmetry. And so we're going to look for ones with symmetry. That's going to be the key to this. Things with the symmetry are the nice ones to do. Whereas the more complicated ones, we may be interested in terms of the answer, but not interested in terms of the calculation. Make sense? They're going to be the same. So calculate the easy one. Do surface 1, not 2 and not 3. But all 3 of those surfaces have the same flux. And the surface number 1, being nice and symmetric, is actually fairly easy. And that's what I want to show you. Let me jump back to that picture of a single point inside a spherical surface. So we call this then a Gaussian surface. Just make a surface, some kind of mathematical sphere around it. And let's apply this equation. Let me do the left-hand side first. That's really what I want to show you. How do you calculate the flux? Well, let me start with this. I'll put my integral. I'll leave the little circle there telling you I got to pick a closed surface, okay? And this is a closed surface. It's a sphere all the way around. There's no edges to it, completely closed. All right, what is the electric field? In fact, maybe I should do a couple of steps starting with the dot product. Because when I do the dot product, that angle shows up there, cosine of the angle. What is the angle? Is it 0? Well, it is here. But what about here? It's still 0 here, isn't it? Because it's the angle between the electric field and the area, right? And so on this side, the area vector points out, but so does the electric field. Down here, electric field points down, so does the area. Over here in the picture, it's pretty obvious. They both point in the x direction. Over here, they both point in the y direction. Coming out to you, and one of the challenges of this class is making sure you see things in 3 dimensions, but coming out to you would be an electric field. And of course, a dA. So you're right, for those of you who said 0, it's not just 0 on part of the surface, it's 0 everywhere. And this is going to be the key to doing our flux calculations. Make them simple. You can make these simple or you can make them real hard. A good choice of a Gaussian surface will make them easy. And one definition of easy is if they had the same angle over the entire surface. And that's why we're going to be looking at symmetries. That's why I said this is a great recipe, but only if you have a lot of symmetry. Because our symmetry is going to answer this argument that I know the electric field is radially outward, so if I make a sphere around it, it's easy to calculate. If I make a cube around it, this would be a nightmare to calculate. A cube, though, I probably could do with a lot of work, but a sphere I can do with a little bit of work, right? But you're right, the angle is there at 0 degrees. So this reduces down to E times dA. Let me keep going with this. Closed. What do we also know about the electric field? Yeah, we learned the equation, didn't we? And we learned that it had to do with how far out you are. And so as many of you are saying, the other nice thing about this is the electric field is going to have the same value everywhere on the surface of this Gaussian surface. And so what I can do is pull the electric field out in front. And now I have a fairly easy integral to do. What is the integral over that closed surface? It's the total area, right? Because I've taken everything out. It's just saying add up the little chunks of area, and you're going to get the total area. So what is the equation for the total area? Yeah. 4 pi r, what do they use for r? Little r? Okay. R squared. Well, now let's go back to what we learned last chapter. What is the equation for the electric field? Coulomb's constant times Q times, or divided by, R squared. Exactly. Oh, getting ahead of myself. And you'll notice something, that the R squared shows up on top, but the R squared shows up on bottom. So notice that the amount of flux, this, does not depend upon how big I made this sphere. Now, does that kind of make sense? You get a feel for this visual picture? I mean, doesn't it make sense that if I were to make this Gaussian surface bigger, how many lines would go through? The same amount. Of course, as I made it bigger, the area would be bigger, but what would happen to the electric field? It would decrease. And the area would increase with the same factor, r squared, as the electric field would decrease, r squared. So it doesn't matter how big you make this sphere. So it wouldn't matter what shape of a surface I put around that charge, and it doesn't matter how big it is, I get the same amount of flux. Exactly. Of course, what I'm after is question mark. What is this number going to be out in front? And so I think we have it now, question mark, because the charge inside is just Q. The Q cancels off, and we end up with Gauss's law, although not in its final form. So we'll keep going, but we've answered what we really need for this chapter, and that is the flux around a closed surface would be this number out in front, which is really made out of three numbers, a 4, a pi, and Coulomb's constant, times the charge on the inside. Now, some of you will probably notice that this is not how it looks in your book. We take one more step. We already know that Coulomb's constant is about 9 times 10 to the 9th. You already know pi's a constant number that goes on. 4, that's a constant number. So let's do this. Let's put all those constants together as one big group so we don't have a bunch of different constants. And for reasons that will be more obvious as we move along, let's call 4 pi times k not just equal to a constant, but 1 over a constant. This constant, as we will see, is really kind of a measurement factor of the resistance of the electric field. It's really saying how well does this electric field penetrate outward from that charge. And of course, we could have had something between this charge and this surface. This charge could have been embedded in silicon because it could be representing some kind of microprocessor in our electronics. And so what we would be asking is how well or how badly does the electric field penetrate or permeate space and get to here. Now, in my case, we have put nothing there. So even though I mentioned silicon, let's just say there's nothing there. So this number out in front here is really saying how well does the electric field permeate free space? How well does it go from this charge out to that surface when there's nothing there? Because later on we'll talk about how well does it go when there is something there. And so we'll have the permittivity of silicon and the permittivity of carbon. And in this case we have the permittivity of free space. And so those of you who have looked at the chapter, which I hope is all of you, you saw Gauss's law written in this form, and that is worthy of the double box and my silly joke. Do you want to know the answers to all the homework problems this chapter? There it is. You will do nothing more and nothing less than that. This is a way to get the electric field. Looking at a surface, pick a surface, any surface. It can be a sphere, it could be a cube, it could be a cylinder, you name it, you pick it, you do the calculations. That will allow you to find the electric field. But I will tell you, some of the surfaces that you might pick will not make the calculations easy, may even make them impossible. So the real key is to study the picture, look for symmetries, and find out what's going to make the calculation easiest. Then you'll find the electric field. And that is the chapter in a nutshell. That is really all it is. My silly joke. Answer to all the questions in this chapter, right there. And so I will start by doing some examples here. Let's see, at figure 12 I have here on my list. Might be a good example to do first. Here's what it says. Let's say that we have an infinite line of charge. Now, again, you're never going to have something infinitely long. We kind of mentioned this with rods in the last chapter. We do this a lot because the reality is when we're building our electronics, we will have a wire, a conducting wire. It may be in the processor, maybe 2 centimeters long, but we are looking at getting close as a micron to it. We have some kind of transistors, maybe thousands of transistors within 1 or 2 microns of it, and we want to know how are those transistors affected by that charge on that wire. And since the wire is tens of thousand times longer than the transistor, we'll just say, hey, it is infinitely long. And if that helps with the ease of the calculation, that would be good for our first generation, and then we can improve our calculations for the next generation and see the added effects and keep building up. And so that's where we are here. We are looking, okay, at a first generation, I got an infinite amount of charge, and so in this brown strip, they are saying this. Let's have this infinitely long strip that is now charged up with some kind of positive charge. And as you'll see, our logic will be the same if we have a negative charge. But can I use Gauss's law to find the electric field from this? And it's going to be surprisingly simple. And this is a good example, not only of using Gauss's law, but why would you prefer to use Gauss's law than Coulomb's law? I wish we had more time. I'd love to do the same calculation with Coulomb's law and just add up an infinite amount of charges along a line. It's not unreasonably hard, but it's got some long integrals with infinite distance and integration by parts, and it takes a few steps to get there. Whereas this, you're going to do under 3 minutes. So, let's give it a try. All right? The first thing to do is to pick a surface. Well, since I called up that diagram, they've already done in blue a Gaussian surface for me. So they picked a cylinder. But let's say we were doing it. Why would you pick a cylinder?
Linear density.
Part of it, I would say, is because the charges are kind of cylindrical in shape. It's a long line. Okay. And so that's probably going to make electric fields that would match the symmetry. And there's where I want to say, even though we do not know the equation for the electric field yet, you have to do half of this problem visually and say, what do I know about this electric field? And so as an example, I like to use this big pipe in here. We got this drain pipe coming down here, but imagine this is this infinitely long line of charges. Okay? Let me stand close versus far. Do you think I'd get the same electric field if I was close versus far? No. I'm further away from the charges. The charges look different. If I stand here, they're real close to me. I stand here, they're far away from me. It's those charges that make the electric field. So I would expect the electric field to be different based on how far away I am. Fair enough? So keep that in mind and see if that's not what shows up in the equation when we're all done. The electric field should change by how far away I am. But let's do this one. Let's say I'm looking straight onto it and I move at an angle. So I'm always the same, I'm still the same distance from it. You might say I'm moving along the Gaussian surface. I'm coming over to some other point on the Gaussian surface. What do you think the electric field might look like here compared to here? I would expect to see the same. Why? Because what makes that electric field is the charges. So again, even though I don't know the equation yet, even though I haven't done anything, I can tell you a little bit about that electric field, knowing that electric fields are created from charges. And so the two things we've already figured out is the electric field I would expect to change its value as I got closer and further, but the electric field would not change its value as I moved along the surface of that Gaussian surface, which is really nice because remember, we need to do an integral. And we do an integral over what? Surface. So is the electric field a constant?
Well, if the charge is in the right middle, then the same distance all the way
Did you catch this? I am going to say the electric field is a constant on a cylindrical Gaussian surface. I am not saying the electric field is a constant, right? Right? Remember, closer, further? Did the electric field change? Yeah, so I'm not trying to say the electric field is a constant everywhere. But what I am trying to say is by looking at this, I would say the electric field is a constant on the Gaussian surface. So when I do this calculation, what could I do with this electric field? Can I pull it out? Because I'm only adding up on the surface. So interesting enough, I will come up with the electric field. That will be an equation. That will not be a constant. It will change with distance. But yet when I do the integral, I'm going to pull it out like it's a constant. Don't miss the difference, right? It's a constant on the Gaussian surface. It is not a constant overall space. In fact, let's take this a little bit further. Let's talk something about the direction of the electric field. I mean, so far, I'll repeat. I'm saying the electric field would change as I get closer and further. I'm saying it would not change as I moved around the same distance away from it. But part of this calculation is going to be a dot product that has an angle in it. All right, let's go back to our symmetry. I ask again, if I stand directly in front of it like here, and it creates an electric field, go on in, and I move over to here, how do you think the electric field here is compared to here? Same magnitude, but also same, and probably best to say same angle versus same direction, because here's what I mean by that. What direction would that be? What direction do you think the electric field would be right here? Do you think the electric field would be, and I'll do a little cross-sectional area here. Let's say we're looking straight down on it. Here's that line of charge. We're looking straight down on it. Here's the electric field, which you tell me the electric field should be the same over there. But I claim that the electric field would not do that. Why not? And yet I haven't even done a calculation to find the electric field. And I'm telling you so much about it. And that's what I'm trying to get across. Half of this problem is going to be very visual right here. How do I know the electric field would not do something like that? Yeah, and there's a couple ways we can answer this. One of you are saying, well, that would make no sense. What you would be saying here is if you stood right here and you look back at the charges, as you look at the charges from the left to the right, aren't they the same left to right? So how would you expect it to create an electric field that is pointing more to the left or more to the right? It couldn't. It would have to balance itself, right? Another answer is doing the same thing is what I call the mental flip. I mean, imagine me standing right here in front of it, and let's just say that the electric field did point that way. And I flip the whole thing over. Okay, so the charges flip over. I flip over. So now the electric field's there. But wait a minute, when they flipped it over, isn't the charge distribution the same as it was before? So how could it be making an electric field this way, and then when I flip it over and have the same charge distribution, it make one that way? It couldn't do that, right? So both of those symmetric arguments are strong arguments to say there's just no way the electric field can be doing this way. The only thing it could do is radially outward. Radially outward. If it was not radially outward, it would make no physical sense. You would flip it over and have the same charge distribution, but a different direction to the electric field. That can't happen. The electric field is created from those charges. Same distribution. A bunch of questions, yeah.
If you weren't permeating through free space, but through an object or material, can an electric field refract?
Yes, yes.
So eventually, in the upper division classes, we'll have to deal with that.
Yeah, okay, fair enough, yes. And to maybe help you a little bit, remember optics is an electric field.
Yeah,
so, So you'll get the same boundary condition, same refraction that we got in our optics as we'd get for our E&M. Yeah. All right, now, here's the crucial point of this. If you're going to find the electric field from Gauss's law, you need to pick a good surface. The definition of a good surface is one that's going to make the integral easy to do. To make it easy to do, you have to know something about the direction and the magnitude of it. So you have to pause and do half of the problem conceptually before you even jump into the math. That's what I'm trying to say. Visual picture. And that's what I've done. In fact, the author's already kind of put the electric field there for you. And maybe I shouldn't have called it up so quickly, because you're going to have to be the ones who pause for a moment to think about how an electric field is created from the charges and get some idea of what you know about the electric field. And I'll just summarize here. Here's what I've learned. I haven't even done a single calculation. I have only looked at the simple knowledge of last chapter that I know electric fields are created from charges. And what that tells me is because I am close here and far here, I expect the electric field to change in a radial direction. But because it looks the same when I am anywhere on the Gaussian surface, I expect the electric field to be the same on the Gaussian surface and point radially outward. And when you know that much about the electric field, the calculation's real easy. And so the hard part's done. Now we just got to do that integral. Yeah.
You remember earlier you had how you had an integral of EDA equals question mark human sine. What is the question mark mean?
Okay, well, the question mark meant I was looking for what number went in front. And there it is, right there. So I've erased it now, but question mark has now become this. And now question mark is gone. I know what it is. Yeah.
Is there any way that you could bend an electric field? Like, or is it all like linear?
Well, remember, the electric field is created from the charges around it. So, yes. And so, this line of charge would be creating an electric field this way. But let's say there was another line of charge right here, which would be pointing that way. So, when the total electric field would then be pointing some combination of the two here. Back here, the electric field would be a combination, canceling, and so I would kind of expect if there's a pole here and another pole here, the electric field would go like this and then bend, as you said, away. And so electric fields don't go in a straight line when there's other charges, because the electric field is the total of all the charges. So yes, other charges would make it bend. And other charges could, as Max was pointing out, could come from other materials like silicon around it. Yeah, because
Frack off of mirror and things like that?
yeah, so and you might refer to that as a refraction instead, but.
So should we learn the value of that constant? Or
Oh, sorry, I meant to put that. So we should know what this number is, right? All right, so maybe I should calculate it for you. So this was equal to 4 pi times Coulomb's constant. And if you get out your calculator and go 4 pi times 9 times 10 to the 9th and take the inverse of it, you will get epsilon naught. You will get the permittivity of free space. 8.85 times 10 to the negative 12. And let's see, what would be the units? Coulomb's constant flipped over, right? And so we must have a Newton downstairs, meters squared downstairs, and a Coulomb squared up there. Okay? And so that, good point, I didn't tell you what it is. And if you know one, you know the other. So if you know Coulomb's constant, you can find the permittivity of free space. If you know the permittivity of free space, you can find Coulomb's constant. I will tell you, though, that I think the better of the two to remember is the permittivity of free space. It is more advanced, going to be more useful for us. We probably will not see Coulomb's constant again. We're done. We appreciate the work you did, Coulomb, but let's move on, okay? This is more fundamental, has more significance and its meaning, and so it's the one I prefer. Obviously, I've done this so much that I also have Coulomb's constant memorized, but I prefer and encourage you. It's the permittivity of free space. You'll see it much more useful. Okay? Now, let's go ahead and answer that question. What is this electric field? So, as I joked but was real serious, how are you going to find the electric field for every problem in this chapter? Start right here. Also start with a mental picture of what the electric field would look like. And then it should fall into place. So, let's do our first calculation here. I'm going to say, start the closed surface, and start by taking the dot product. Why don't I do the left-hand side first, since it does involve the integral, and I think the harder of the two calculations, and the one that I want to make sure you see, so that as you start working on them tonight and come talk to Don over the weekend, and you hang out on Friday night and Saturday night and Sunday night and Monday night, and get about half the homework done, you will see how to do this. All right? And I'll start with this. Like I said, I think we've done the hard part, and the hard part was looking at the picture, looking at the symmetry. What is the angle between the electric field and the area vector?
0.
Yeah, and the reason we went through this long discussion is over this rounded part, what I call the face, the angle is 0. If I may, I'm going to give myself a little more room and erase this. And say, Gauss's law is a closed surface. Do you see three surfaces here? Right? I have this rounded part, the face. But I also have the top of the cylinder and the bottom of the cylinder. And so just like that cube, we did 6 faces in order to get the whole closed surface of the cube. We have to look at this cylinder and do the 3 surfaces. And so those of you who told me the angle was 0, you're right, but what you meant, it was 0 where? On the face part of it, right? What's the angle on the top? 90 degrees, good. So everywhere on the top, dA is pointing up, but the electric field is radially outward. So this is 90 degrees. And what about the bottom? Isn't it 90 degrees too? Because again, electric field, the area is down and the electric field is radially outward. And of course, maybe not a surprise, probably something you overlooked or was so obvious you didn't even question it, how much flux does go through these top and bottom pieces? 0, right? The flux is going radially outward. It's skimming the top part and the bottom part. So that's why we could just say, ignore that one. But hopefully you see we can't really ignore it. We want to make sure Gauss's law is a closed surface. It's every surface that encloses the charge. Okay? And so I'm going to put it up here, even though they come out to be 0, to show you that I thought about them and I analyzed them. Yeah?
Doesn't like a charge like in the middle of the cylinder, like doesn't it kind of also go 3-dimensional, like up?
Oh, let's see if I understand. You're saying a charge here?
Yeah, doesn't it go up through the top at all, or is it only?
Okay, if I looked at just a chunk of charge in the middle, last chapter, Coulomb's law, I would say that the electric field, let me draw it as a picture here. Over here. If I looked at this chunk right here, I would say yes, the electric field from that chunk over here on the top is pointing something like that. And for that matter, down on the bottom, it's something like this. Fair enough. Okay, but remember that if this distance is, say, 3 centimeters, then there's another chunk right here which would be creating an electric field that way. And so what happens to the vertical components? They cancel, and the whole electric field is radially outward and has no vertical component. Good point. This argument only works if it's infinitely long. Exactly. If this was not an infinitely long rod, that argument would go away. The direction of the electric field would be unknown. This integral I could not do. I'm stuck. Do not do it with Gauss's law. Go back to Coulomb's law and add up the rod that is finite in length. So I would say if it's finite in length, do Coulomb's law. If it's infinite in length, do Gauss's law. Yeah. And so again, different choices for different situations. Yeah.
How did you know that the charges are uniform?
Oh, I guess I should have said it was a uniform charge distribution. That was given in the example. And so again, if you have or get your chance, I think this is the first or second or third example there in the book, and they say an infinitely rod that is a uniform charge distribution. Okay. Okay, so you've answered this and this. Good. Let's come back to this one. I've got E times dA here, and again, that is 0 degrees. Cosine of 0 degrees is 1. And so maybe I'll move over to this side of the board, kind of working backwards. But now I have E dA over the face equals charge inside over epsilon naught. And we answered this part earlier too. What did we say about the electric field on the face? It's constant. So I can pull it out. I do not know the equation for the electric field, but it's outside of the integral, and now I'm going to find it. That's why we're doing Gauss's law, to find that equation. What is the equation for the electric field? But notice again, I couldn't even have gotten this far unless I already knew something about the direction of the electric field and something about the strength of the electric field being a constant on the Gaussian surface. So I did that much, which helped me to get this far on the integral. Now I can do the rest of it, because what is the area of the face? Yeah, as you wrap a cylinder, it's the circumference, 2 pi r, times the length of the cylinder. And do they list it as in little l? Yeah, so we got little l for the length. We got the circumference of 2 pi r. And so there is all my calculations on the left-hand side. Let's go over here to the right-hand side for a moment. On the right-hand side, we are supposed to find the charges inside. Now I'm going to emphasize that. Inside. Don't worry about the ones outside. In fact, how much charge do I have total? I have an infinite, right? I've got a rod that's infinitely long here. And so again, that part of the equation is not saying how much total charge do you have, but how much do you have inside the Gaussian surface. And that I do not have a total amount. In fact, let's use what we did in the last chapter. Let's refer to the amount of charge per length as lambda naught. That's the charge density. So if I multiply it by the length, that will tell me how much charge is in there. And it makes sense that it would depend on the charge density. More charge density, I would expect a stronger field. Less charge density, a lower field. Yeah.
Can you explain that again, the lambda naught L?
I'll come over here. What is lambda? Lambda naught is the amount of charge per length. So if I move length over to here, length times lambda will give me how much charge. And that's what I did, how much charge. But notice again, I only use the length of the Gaussian surface because I only want to know what charges is inside my Gaussian surface. Notice again there's an L on each side that will cancel off. Now that shouldn't surprise you because L is the size of the Gaussian surface. That's just a mathematical tool to figure out what the electric field. The electric field should not depend on the size or the shape of your Gaussian surface. That makes no sense. So the fact that they cancel off doesn't surprise me at all. But what I'm left with at the end of all this calculation is E, the electric field, equals 1 over 2 pi epsilon naught lambda over r. And there is a significant calculation. If that made sense to you, you will do okay. You will work on these and just every other shape will work out. It'd just be a different shape. Okay? And so that is the electric field. And then notice what I have when I'm all said and done. Doesn't this equation then say that the electric field does change with R? And the smaller R is, the stronger the electric field. And so it does match what I suspected from the very get-go, is that if I was close, I would have a strong electric field, and as I got far, I would have a weaker electric field. It does change with the radius. And so, yeah.
Just for mathematics, when you do your integral, are you just doing it from 0 to L? Because your R remains constant as long as you want your charge to remain constant?
No, I am. It's an area.
Okay.
So to do an area, the easy way to do an area is to say this. I'll write it as you said. I've got an integral of dA over the area. So you might say I am going to start with 0, add up chunks until I get the total area of the face. So an integral of dA is A evaluated from 0 to the area of the face. And so that's the area of the face. And how do you get the area of the face? 2 pi r times L, right? I think what you were asking is more of a double integral than a single integral. You were saying something like, if I wanted to get the area of something, I would add up my x's and y's, and in this case,
Adding up disks.
right. But you will notice that I avoided this for 2 reasons. And what doesn't need to be that hard. Number 2, this just means add up all the little areas, you're going to get the total area. Then we can go right to geometry. What is the area of the face of a cylinder? And we don't have to do a double integral in terms of our calculus. Oh, the other reason too is I promised you guys that we would not do any math above 160. You don't get to double integrals till 200. So we camouflage the double integrals as geometry, and we do it mentally. Or when we have one we can't camouflage, we just do a single integral twice and tell you it's not a double integral. Yeah. All right. So, but again, I want to encourage you how visual this needs to be. Okay. All right. Well, we've done one good example. Let's go to the next one here. I think the next one the author does. Actually, I think he did this one before. Yeah, I did that one first. Let me jump to this one. Number 10, or figure 10. And he did this example first, but it's another good example to do. Instead of having an infinite line of charge, let's ask this question. What is the electric field from a sphere that has size? Not a point charge. See, we did that last chapter, right? Didn't we learn what the electric field is from a single point? And then if you gave something size, you had to chop it up at an infinite number of points and do an integral? And again, a ball, a sphere, if we spread the charge out uniformly in it, we could ask ourselves, what is the electric field on the outside of a ball? And something we didn't ask for a point, we could ask, what's the electric field inside? And again, this one, if I had more time, would be brutal to do with Coulomb's law. Will be trivial to do with Gauss's law. At least as long as you see the technique of Gauss's law and how you get the direction of the electric field and the strength of the electric field. So let's try another example here. All right, so I'm going to come over here. And I'm going to put on the board what I ended up needing space for and erasing, but the flux calculation on a closed surface will equal the charge inside divided by the permittivity of free space. That is the point of this chapter. Use that again and again and again. The hard part may be also deciding, should I do this problem with Gauss's law or should I do it with Coulomb's law? I will tell you for this chapter, do everything with Gauss's law. That's the point. When it comes to the test, that's a harder decision, because when you get that problem on the test, you're like, he wants me to get the electric field. And by that time on the test, we've got 3 techniques. Right now you only have 2. But you've got to make a decision. Which one will get me to the answer within the 2-hour time limit I have? Because one will get you there fast. And the other options will take hours to get there. And you don't have hours to do the test. You've got just 25 minutes to do each problem, right? Is that what it comes out to be? 25 times 5, 125, yeah. So you've got 25 minutes per problem. Okay, so part of your skill is recognizing why we have the 3 different techniques and which one is to our advantage or disadvantage. And I do claim that this one, with a lot of symmetry in it, is to our advantage to do Gauss's law. So let's look at the electric field from a ball. So here's this brown ball, if you will. The ball has a radius of A, and what we're going to do then is fit charge evenly throughout it. Okay? And so there's chunks of charges inside and all the way out to the edges of the ball. This thing has charges. Okay? Let's apply this. Again, let's do the hard stuff. Don't even start the calculation. Let's look at the direction of the electric field. Okay? Let's start on the outside for a moment. So imagine, and I don't have a good big hanging ball here, but imagine a giant ball hanging right here, and I stand away from it, and if I am close versus far, do you expect the electric field to be the same? No. The charge distribution looks different in the sense that when I'm closer, it kind of fills my whole sight of view, but as I get further, I'm farther away from them. They're harder to reach, but the field of view is smaller. There is something that looks different, and because of that, I would expect the electric field to be different and to change with distance. So keep that in mind. I hope when I'm all done, I will come up with an equation that says the electric field does change with distance. But now, like we did on the last one, let's move around the ball. Again, got a big ball over here, and if I go a certain distance, and I stay that distance, and I move over to here, what would I expect the electric field here compared to here? Yeah, the same, because again, I'm looking at that charge distribution, and it's the charge distribution that determines the electric field. And since it looks the same, and it looks the same left or right, I expect the electric field here, as well as here, to have the same magnitude. And what direction? Radially outward. You would say the same direction. As I look here, and I'm looking right towards the center of the ball, I see charges on my left and my right, so I would expect the electric field that it creates to be pointing radially outward. Not more to the left, not more to the right. If we want to do the flip thing again, that's fine, right? If it was somehow creating an electric field that was slightly to the left, and you take that big ball and you flip it, now all of a sudden the electric field is going to the right, and yet when I flip that ball over, I have the same charge distribution. How could the same charge distribution first make one to the left and then to the right? It makes no sense. And that's why it wouldn't do that And so this electric field, and that's why your author is suggesting, and I am too, when you draw a Gaussian surface, draw a sphere around a sphere. Because I know that the electric field has the same value everywhere on that Gaussian surface. And I know it's radially outward. And that's going to make the easy part come into play, the calculation. So here we go. We will do a spherical surface around it. And I will start with the dot product first.
What number is this?
It's an example in the book. Yeah. Which example is it?
24.3.
Okay, so third example. Yeah. And so let's see if we can do this left-hand side first. And now I think you're starting to get the rhythm of it. These go real fast once you get a good Gaussian. Once you see mentally what the flux will look like. Because you already told me this indirectly anyways. What's this angle? 0. It's 0 degrees everywhere on the Gaussian surface. This picture doesn't really show a three-dimensional picture, but remember, this is 3 dimensions, and the Gaussian surface comes out of the screen here and into the screen, and the electric field is radially outward, but also so is the area vector. So everywhere on that surface, the direction is 0. What about the electric field, as we argued? It has the same value everywhere on the Gaussian surface, and I want to emphasize that. I am not saying the electric field is a constant everywhere in space, but I am saying the electric field is a constant everywhere on the Gaussian surface, and that's what I'm integrating. So I'm going to pull it in front of my integral for the surface. All right, then, not worrying about the double integral or the limits, what does this mean? Closed. This means add up all the little areas that make up your surface, so you're going to get the total area of your surface. If it helps, maybe I'll put it A of my surface. But what is my surface? It's a sphere. And so I'll have to go back to my geometry. What's the formula for the area of a sphere? It's not 4/3 pi r cubed. That's volume. What's the surface? Yeah, 4 pi r squared or a squared?
For our Gaussian angle, R squared.
R squared or a squared?
So it's the area of the Gaussian.
It's r squared. Remember, I am trying to find the area of the Gaussian surface, not the area of the surface of the ball. At least at this step, that's what I'm trying to find. There might be another step where I want to know the area of the ball. So don't confuse those. But for this step, I want to know the area of the Gaussian surface. And so it's definitely an r squared. All right, so there's the left-hand side of the equation. Let's go to the right-hand side of the equation. The right hand says that it should be the charge inside over epsilon naught. I'll leave the epsilon naught, the permeability of free space, alone there for a moment, and then go inside. Well, how much charge is inside my Gaussian surface? Well, the easy answer is all of it, right? I mean, they're trying to say here that I have all the charge in there, Q. So why don't I just make it a little simple and just say Q? Nothing really to work with. You could have done this. Remember how we've used the symbol lambda for the charge per length? And we also saw only one time a symbol sigma that we like to use for charge per area. Since this is three-dimensional, we could call something the charge per volume. And I haven't had a chance to use it in class, but we like to use rho, and I know you've seen it in the book as you were doing the reading, but rho is kind of the standard symbol for saying how much charge per volume. Because if you wanted to do it that way, you could get the total charge by saying what is the charge density times the volume. So you would go rho, and I would suggest not to do this because there is no rho in that picture and the Q is so easy. But I do want you to see this. What would be the volume? So it's not surface area. It's not 4 pi r squared, right? It's volume. 4/3 pi a cubed or r cubed? A cubed here. 4/3 pi a cubed would be the charge inside. Why a cubed? Exactly, I'm looking for where the charge is. The charge is only in the volume of the ball, not the volume of the Gaussian surface. The Gaussian surface is something that I mathematically are thinking about, something that I have drawn bigger than the ball. The ball itself is where the charge is. So I want the volume of the ball. Okay. Now again, I only do that so it can bring up that discussion of when do I use an A and when do I use the R, and make you think a little bit about the meaning behind it. Don't just do the math, read the math. You know, I've joked with you many times that you need to see and read the math. Otherwise, if you just becomes, hey, I'm going to learn the formula, I'm going to plug and chug. And I've joked with you and said, well, if you do that, you'll do okay. You'll get an okay grade, transfer to an okay school, have an okay career, find an okay spouse, have okay kids, right? Okay. Because again, if you just plug and chug, you will miss something far bigger. You won't see the interconnections here. And that is more true in this chapter than maybe any other chapter. You have to be understanding what is going on. And then it's just a simple choice of, well, of course it couldn't be R, it's got to be A. It's got to be A because I'm looking for the charge that's inside, and the charge is inside the ball. So of course I would use an A and R. Why would you even ask? That's a silly question. And I'd ask because a lot of students like to plug and chug. And get okay and get a C grade. You know, you're only going to lose a few points for it, so why not? I'm not sure which one it is, you know. But it will make a difference in the values we get, the relationships we get, and of course the engineering we do here. Well, I'm going to leave that alone and come back to here because this is really how I'm going to write the charge, at least for the moment, as just the total charge Q, not even mess with density and A cubed. That was a kind of a side discussion to see if you were kind of getting the picture and the meaning of the terms in Gauss's law here. But what that does is it allows me to finish and answer the question that we got started here. What is the electric field on the outside of a ball that has a uniform charge distribution? And what it comes out to be then is 1 over 4 pi epsilon naught Q over R squared. If you kind of remember that this is Coulomb's constant, you may not even be surprised when we're all done. What is the electric field outside the ball? It's the same as a point. So it's kind of easy to remember. You have a uniform charge distribution. If it's a point, we got that equation. And now we're proving that if it's a ball, that really doesn't change anything. And maybe you can see it too, because if you were to stand over here, you could argue that that's not a point. These charges are closer. But these charges are further. These charges are to the left, and these are to the right. And it's the equivalent of all of these being at a point. It's why those of you who've already done the lab, and another third of you will do the lab this afternoon, we were asked to measure the electric field from a point charge. Did we have a point? No. We got a ball about this big out there. And it's going to give you the same electric field. So whether you have a ball or a point, you're going to get the same electric field. And so that's what we got out of this. And I should emphasize, as long as the charge is evenly distributed. Because if it wasn't evenly distributed, I would have been in trouble back here because I wouldn't have made this argument. I wouldn't have been able to pull the E out in front. And likewise, I wouldn't have been able to argue that some charges are closer, but just as many are farther. And so getting the electric field from something that varied within the ball would be a lot harder. I certainly wouldn't try to do it with Gauss's law. I'd probably try to do it with Coulomb's law. And then I probably would have to add up every little point. And then I probably really would have a triple integral, which is why we won't do it in this class. We will wait till your upper division E&M and give you a ball where you will actually do the triple integrals. And then in that case, your teacher will tell you, hey, we are not just doing math 160. We are going to do math 200 and math 220. And we are going to make you do it day and night and day and night. But right now, we're just trying to get you Calc 1 and Calc 2. All right. So that's what you have to look forward to for those of you who go into physics or electrical engineering, and probably you guys in mechanical engineering probably won't have to have an upper division E&M. So now let's go inside the ball, because here's where it gets more interesting, and you can see the power of Gauss's law if we go inside. Yeah.
So, because people we didn't use the rho times force rates by a.
Oh, okay, if you would prefer, I could call the total charge rho 4/3 pi a cubed, if you like that.
Okay, so you're just.
But see, the rho was not given in the problem. And again, the general idea is you give answers in the symbols that were given. So the rho was something I kind of created along the way, partly to show you the difference between A and R, and partly to get you ready for the next calculation we're going to do.
Okay. So
but the answer really should have a Q in it, because that's what was given in the problem.
Oh, I see. Okay.
Yeah. Way in the back.
Is the point charge of the solid object always located in the center of mass of the solid object?
No. The charge, if you had a solid object, an insulating solid object, we said about insulators, the charge could be anywhere you put it. So I don't have to put it in the center.
Like you said, the charge of that solid sphere is equal to.
Right, so I'm saying it's equivalent to. I am not saying that the charges is all at this point right here.
Gauss' circle.
What I'm trying to say is if I had all this charge on a single point, and that point was located at the center, I would get the same electric field. So in that sense, it's the same. But if I had charges that were not evenly distributed, then I would get a field that looks very different than if I just had a point charge of Q at the center. And of course, how different would be depending on how crazy the distribution is. But we're not going to do too much of that, because again, that's next semester, or the next level of class. Okay. All right. So if I may, I'll erase this. And if I may, I'll erase this, because again, I like to look at the electric field in terms of the permittivity of free space, not Coulomb's constant. And so that is our electric field. As I said, let's make this next step. Let's go inside now, and that's what this picture B is for. Really do the same thing. So I'm going to put next to this equation that this is valid for any value of R greater than A. That's outside the ball. My logic would be exactly the same if I was outside the ball, but inside the ball, my logic may change, and it will change. And so again, something that would have been extremely difficult with Coulomb's law is going to be really easy here to do with Gauss's law and get inside the ball. That's why last chapter we didn't even talk about what's the field inside the ball. We were waiting for this one because it's going to give us an easy way to get what is the field inside the ball. But again, let's do the hard stuff first. The hard stuff is the symmetry on this ball. So imagine now that the center of the ball is, say, right here, but the ball is bigger than this room. So I am in the ball. All right? So as I stand right here, looking at the center of the ball, realizing that there's charges everywhere around me. No, solid. Solid. And don't ask me how I'm going to get into the center of this solid ball. Okay, but imagine yourself in the center of this solid ball. There would be charges in front of me towards the center, and then of course charges beyond that. And there would be charges behind me.
How do you have charges in the center? Can you go on the surface since it's solid?
No, why would they on the solid? It's an insulator. They stay wherever I put them. So I make a little piece of plastic and I rub them. I pour a little more plastic, let it cool, rub it, pour a little, like we did in class with the rubbing. I rub it, put a little more plastic, rub it, put a little more, rub it, rub it, rub it. And so there's charge everywhere in here. And they stay there. They don't move to the outside. We're probably not going to get that far today, but if this was a conductor, they would flow, they would move. They wouldn't stay where I put them. And what we're going to learn for conductors is they will move to the outside. And so obviously, I shouldn't say obviously because we haven't discussed it yet, but this could only be happening with an insulating material. So this could be our vinyl or our acetate, but this is not the aluminum pit ball. The aluminum pit ball, they're on the outside.
Yeah.
Right.
They're all on the outside.
Right. This is an insulator. All right. So again, let's just say I made it that way. I get a piece of plastic, small, rub it, another, pour, rub it. I got charges spread out. But now, mentally, picture yourself in the center of this ball. There's the center of the ball. If you move out away from the center, would you expect the electric field here to be the same as it was there? No, I would see charges very differently here. When I get way over to here, most of those charges are now on this side of me, and there's very few left on this side of me. In fact, when I'm at the center of the ball, what would I kind of expect about the field? I would expect zero, right? I mean, I'm standing here and I see a bunch of charges to my left and an equal balance to the right and an equal balance above me and below me, in front of me and behind me. And so whatever electric field these create, these over here create the same and they cancel off. And I expect to get a zero electric field in the center. And maybe as I move a little bit outside of the ball, I kind of expect the electric field to kind of get stronger. Because as I move this way, I have more to my right than my left. And the more I do this, the more I have on my right. And I'm kind of expecting that the field is going to change and get bigger and bigger as I move from the center of the ball to the surface of the ball. Right? So I do expect it to change with the radius. But again, let's walk around the perimeter, if you will. I'm inside the ball. There's the center of the ball. I am 1 micron from the center of the ball. And I move so that I am still 1 micron from the center of the ball. What would I expect the electric field to look like? The same strength, right? Because I would have the same charge distribution. What I see when I'm here and what I see over here is really the same charge distribution. And so just like we did on the other two examples, I would expect the electric field on a spherical surface to be the same and to be radially outward. Knowing that, I've done the hard stuff. Now I can do the easy stuff, or maybe I should say the easier stuff. Let's actually do this integral. And so I would start off and say, let's take the dot product. And just like we did on outside of the ball, we argued that that angle would be 0 degrees. The electric field would be radially outward. And my surface would be radially outward. What would I say about the electric field inside the ball at the, on the Gaussian surface? And I expect it to be a constant. And so my first step here is a lot like all the other first steps I did. Pull out the E, put the angle 0 degrees, got an integral of dA. Which makes then the integral real easy to do because then this would be the integral of dA is just A. Maybe the harder thing is to say what A? Surface of what? Okay, so it is a 4 pi. Yeah, it's going to be the r squared, using the r for the radius of the Gaussian surface again. It's just now r is smaller than a for this case. And so it still, though, is represented with a r. So it's 4 pi r squared. Now it's different here.
The charge, because it's coming from a smaller size.
Yeah, let's look on the right-hand side. It's charge on the outside and charge on the inside. There's both. And so what do I want? Gauss's law says only need to worry in your calculation about the part that is on the inside. So can I put a capital Q here? No. I can't, can I? Bummer. Because that sure made last one's real easy to do. So what am I going to do instead?
Find that volume of that.
Good. I will integrate, right? Why don't I do the following? And this one, well, we could either integrate or do proportions. Maybe I should do an integral, since number one, you are familiar with integrals. Number two, integral would work for any case. Proportions would only work if it is a uniform distribution, which it is. But let's do the integral. Let me do a side calculation here. If you can imagine saying how much charge is on one ball, another ball, another ball, another ball, another ball, another ball, another ball. If you add up all these, what I call shells, these spherical shells, another shell, you get the solid ball, right? So I'm saying this, the total charge inside would be an integral of dq. dq is adding up all the charges as I make layers to make this big ball. Let's use, and I erased it here, but as I said, it's kind of nice to talk about charge density at this point. We said charge density is just this. How much charge do you have in a given volume? So let's take a little bit of charge inside a little bit of volume. If it's a uniform charge density, the whole charge over the whole volume, which we talked about a few moments ago, would be the same as a little charge inside a little volume. The reason I like that is because a little volume times times density would give me my little bit of charge. And so dq is rho dv.
Can you divide dv to dA times something else?
Hang on, let me put this in here. So this becomes rho dv, right? So dq times rho dA. You saw me do something very similar to this last Tuesday at the beginning, where we used Coulomb's law to find the electric field from that semicircle where the charge distribution changed, and we had to find the total charge on there. That's what I'm doing here, except now I'm doing it in 3 dimensions instead of 1 dimension on an arc. I'm saying find out how much charge. And so to find out how much charge, I take the density times the volume. Here's what's nice about this integral. Here's what makes this an easier problem. What do we know about the charge density for this case? Yeah, it is the same amount everywhere throughout the ball. And if I do that, I can pull it outside of the integral, which makes it an easy integral to do now because, whoops, I forgot my integral sign. Because the integral of dv is just v. And so the charge inside is just the density times the volume. But here's what I want to point out. I just did the easier of the cases. Because of course, we're still learning along the way. What if the charge distribution was not constant? You couldn't have pulled it out, right? You would have to be told what the equation is and leave it in here and do the integral. And so you will do those rarely, but at least can get you started for your next level of where we kind of get to the harder ones and more realistic ones where the charges are not evenly distributed. They have been injected in the center of the ball and they migrate outward, and they don't migrate evenly. They are very concentrated in the center. And then due to temperatures and vibrations, they migrate out and they have some kind of functional form as they get out. And we would have to know that functional form, and we'd have to put it in here and do the integral. But again, we'll build up to that. But what I do want you to be careful about here is saying that the charge inside is density times the volume means you are saying that the density is uniform. And so there'll be many times where this will work for you, but there'll be some times where this will not work for you. I'm trying to point out why it works this way. It works this way because the density is a constant. So I could come over to here and say that the charge inside this ball is the charge density times the volume. And when I mean volume inside, I'm talking about the volume that's inside my Gaussian surface. That's the charge that's inside my Gaussian surface. But again, I'm going to use this equation, but with justification that it works this time. And I'll say it even works most of the time at this level. But there's a few times. And when you transfer and go to your next level, you'll probably seldom ever see this equation being valid again. You'll get more realistic ones where the charge distribution changes. All right, well, keep it going down this right-hand side. See if this makes sense. What is the volume? 4/3 pi A cubed or R cubed? Oh, I'm so glad we had this discussion earlier because none of you have any doubt about which one it is, right? And this time it is R cubed. It's R cubed this time. Why? Exactly. I am looking again, want to emphasize this. You are looking for the charge inside the Gaussian surface. Now, is there charges outside the Gaussian surface? Yes. But as we started this discovery of Gauss's law an hour and a half ago here, it was trying to point out that we only care when it comes to the calculations. Don't get me wrong, the whole electric field is created by all the charges. But when it comes to the calculation, we only want the charges inside. And so inside the Gaussian surface is R this time. Yeah?
That's assuming that it's constant. If it wasn't constant, would you do A cubed? Would you do the outside minus the inside?
I think what you're saying is if the ball was hollow on the inside, I would have like an R cubed minus an inner radius cubed. Now, if the charge was not uniformly distributed, I would have never done this step. I would have had to know how the charge is distributed, put in the equation, and done the integral. And so that would be a more complicated one. But it wouldn't be something as simple as an R cubed minus an A cubed. Yeah, that's the volume for a sphere that's been hollowed out on the inside. Okay. Okay, well, I'll keep going because what is at least nice here is a couple of terms show up on each side, like a 4 and a pi and an r squared, a 4, a pi, and an r squared, leaving me with the electric field equals the density times the radius over the permittivity of free space. Sure? And now, hopefully, it fits what we got started in this problem 10, 15 minutes ago. Didn't we say that if you were at the center of the ball, what did you expect the electric field to be? 0. What does this equation say? Yeah, if R is 0, if you're at the center of the ball, you're going to get 0 electric field. And what happens as you move away from the center of the ball? Gets bigger and bigger and bigger and bigger and bigger. Exactly. And at least until you get to the surface of the ball, which at this point, this logic doesn't apply. We got to go back to this equation. Now, I'm not quite done. I want to do one more step because what's bothering me about this one is I have rho in it. And rho is something I invented or created along the way to help me, but it wasn't listed in there. So I think it would need the next step here to really be complete. And so let me continue on. I'll leave this one here because I want to see how these two compare. But that was the equation we got for outside the ball. And so I'll go E equals, and I got the denominator. I'll leave that alone for just a second. But I got the density. Okay. How can I replace the density with the things that are given in this problem? Right. Why don't we do the whole charge divided by the whole volume of the ball? So Q divided by 4/3 pi A cubed or R cubed? Yeah, and this must be the A cubed, right? This is, the density is all the charge over all the volume, not the volume inside the Gaussian surface. Don't mix those. Easy to do, but you're getting better at it, right? And I guess I have an R here. All right, so this does reduce a little bit. It looks like this 3 up here will cancel with that 3 down there. And this then becomes total charge Q times R times 4 pi epsilon A cubed. Maybe better written for me anyways as 1 over 4 pi epsilon naught. That's the Coulomb's constant part of it. And then this is the variation I get away from a point charge. And so I have an equation, one that we haven't seen before, that says that the electric field at the center of the ball would be 0, and it would increase until you got to the surface, this equation being valid only for those radii less than the surface of the ball. And then this equation being valid for outside the ball. And so as we go to further chapters and we need to know the electric field, because this chapter we're learning how to find the electric field, but you're going to need these equations for later on. You're going to remember, am I inside or outside the ball?
So this wasn't asked in the problem, but what would we expect if R equals A if we're actually on the surface of the ball?
Oh, now, okay, if I'm actually on the surface, I guess I would expect my logic from inside and outside to match, right? And so let's see if these equations do match. If I was on the surface of the ball, this would be an A squared. If I was on the surface of the ball, this would be an A, canceling with 1 down there, and I get the same equation. So inside the ball, I would see a linear relationship to the electric field, right? The electric field gets stronger with R. When I get to the surface, either equation would be valid, so maybe I could even put, greater than or equal to with less than or equal to, and I'd get the same value at the surface. But once I got outside the ball, the electric field would taper down and get weaker because of the 1 over R squared value, as we saw for point charges. So as we talked about, this is the same for a point charge. So we expect it to get weaker as we get further, and we expect it to get bigger. So the strongest electric field would actually be on the surface of this ball if we could get inside and move around.
In the answer, isn't that 1 4 pi epsilon? Isn't that just Coulomb's constant?
Yeah, and if you wanted to change that back to Coulomb's constant, so you're only writing one constant, that would be fine. But I will tell you, you probably won't see it written that way by me or the author. We're going to start using the permittivity of free space. It has a deeper meaning to it, and that's... All right, well, I'll keep going because, again, all I want to do is a bunch of examples and as many as I can today, and then it won't be enough, so we'll have to do more on Tuesday. We'll see how you guys do over the weekend.
Isn't there a volume R where the area of the little sphere is equal to the outer shell that's left?
Yeah, then that was his question on the surface, right? Right here, when little r equals A, the surface area of the Gaussian surface is the same as the surface area of the sphere. Is that what you were saying?
Yeah.
Yeah.
I mean the volume. The volume of the little sphere is equal to the outer volume.
Okay, volume would be the same at the surface.
Would the electric field cancel out from like?
No. Not, the electric field would cancel out in the center because the volume to your left and the volume to your right are the same. I think that's what you're trying to say. That all these charges on my left make an electric field that way. All these on the right make an electric field that way. Fair enough?
And also, why is it 0 if it's a conductor? If you go inside.
Because they cancel each other.
Let me hold off on conductors. Shoot, I think that's the part I haven't even mentioned, but I will tell you that, and your author does it at near the end of the chapter, and that's where I'm not quite there yet, but for a conductor, the charges will move out to the surface. And I haven't proved that why. But I do want to try a little bit harder one to make sure you see this. Because if these were all making sense, hopefully this will make sense. And if this makes sense, there's probably nothing in the chapter that won't make sense to you. Here we have a ball of charge Q, uniform charge inside the ball of radius A. That's the stuff we just did. Then we surround the ball with a shell, the blue shell. And the blue shell has a charge of negative Q. What is the electric field? Everywhere. Inside the ball, between the two objects, inside of the shell, outside of the shell. Questions?
Yeah. What we did before was an insulator. But you said for a conductor, we've got force on each.
Yeah, because I really haven't given you enough to do conductors yet. Yeah.
Why on the graph does it say it's greatest at the surface?
Why is it greatest?
Yeah, electric field is greatest at the surface.
Now, are you asking why mathematically? You're asking why conceptually from the physics? Well, this first part right here is a graph of this equation. It's got an R. E is proportional to R. That's the equation of a straight line. So I've drawn a straight line until I get to radius A.
So that graph's not for both.
Yeah, so this is the part of the graph for that equation. This is the part of the graph for that equation. I have got two different equations. I've got to use different equations under different circumstances. Am I in the ball or am I outside the ball? So when I put them together, what I guess math you call piecemeal equations, the two of these equations piecemeal together represents one equation for everywhere in the ball, inside and outside. But it's two equations. It's one equation that is valid when you're inside the ball, and it is another equation that is valid when you're outside the ball. Does that help? All right. So in the very short time we have left, can we do this more complicated problem? And start with area 1. Inside that ball. And so I will put, well, I should probably call it volume 1. To remind myself and you, it's 3 dimensions. I know when it looks on their screen, it's 2 dimensions. But in volume number 1, we are inside that brown ball. Could you give me the electric field inside there? This is no different than what we just did. How does adding a shell on the outside change anything I did on the inside of the ball? It does not, right? Now we better stop and think about it, make sure it doesn't. But remember, our argument in order to do Gauss's law was that the electric field had to have the same value when you were the same distance away. And I claim that if you could imagine yourself standing somewhere in this ball and looking at the charges all around you, including the charges of this shell, if you made a little circle or a little loop, they would still look the same everywhere. And so the logic of the electric field would still tell me that it's radially outward and that it's a constant on the Gaussian surface. And here's the best part of this. When I go to do a calculation for a Gaussian surface, what charges do I care about? Only the ones inside the Gaussian surface. Even if I have charges on the outside, that's fine. They contribute to the whole electric field, but they're not going to change my calculation. So, if I were to write this out, and I'm going to have to do it fast, I'm not going to write it out. Wouldn't I just write the same thing? Question?
So if we had a single charge except for the ring around it, you couldn't use the same formula?
Well, if I had a single charge instead of a ball, you mean?
For the blue part around it.
Oh, instead of, if I just had a single charge right here? Oh yeah, then I wouldn't even be able to use Gauss's law. Because I wouldn't be able to argue that if I was, so let's say there was a charge right here, and if I was standing here and I went along an arc here, let's say I went from here to here, the charge distribution would look a little different because that would be at a different angle to me. And I could not argue that the electric field would be the same here as it's same here. And because I can't do that, I can't pull it out of the integral. If I can't pull it out of the integral, I'm stuck. And the integral will get me nowhere. So, Gauss's law, I'm stuck. Go do something else. But I don't have that purposely, because I do want to use Gauss's law here. And what I'm trying to say in the short amount of time I have here is if I draw a Gaussian surface, so that the Gaussian surface has a radius of less than a. So, volume 1, when r is less than a, I would go through exactly the same argument, and even though there's charges on the outside, I would still say it's symmetric. I would only focus on my calculations on the one on the inside, and so I would come out with exactly that same formula. And there it is. Might be surprising a little bit, because wait, didn't we add charges? Doesn't that have an effect? Well, number one, no, not in the calculations. It's only the charge on the inside. Physically, does it have an effect? Well, an effect that cancels off. Because look at this. Let's just say this brown ball wasn't here. And you are standing somewhere inside of the blue shell. Wouldn't you get an electric field from this side as well as this side? And if you're in the center, you'll say, oh, those are easily going to cancel off. But I'll do you one better. Anywhere inside of that shell will cancel off. If I draw a shell and put a bunch of charges on it, most people see right away that the center of the shell is going to cancel. You have equal charges left and right. But if you get closer to one side of this shell, and maybe you draw two intersecting lines, so you take that shell and divide it into 4 pieces, 1, 2, 3, and 4. These two on top and bottom, I think, are easy to argue. Hey, they're going to cancel off. They're exactly matching top and bottom. But are these two going to cancel off? And I agree that that's not so obvious, but they will, and here's why. Less charge here compared to here. But you're closer. The amount of area over here increased as r squared. The field got weaker as 1 over r squared. And so anywhere inside this shell, amazingly the electric field is going to cancel off. So not a surprise that the equation I got for inside the ball, even though I added a shell, even though that's giving me a bunch of electric field inside of the ball, the electric field from the shell is canceling off. And that's why it came out to be the same thing. And it looked like it was going to be hard. Yay! How about outside the ball? How about what your author calls volume number 2, where R is greater than A, but less than, I think B. I don't want to get B. Yeah, less than B. What's the electric field? Yeah, and hopefully you caught that same argument there, that even though I put a shell on there, if you look at the math, none of the charges from the shell are inside, and it's still spherically symmetric. So when I go through Gauss's law, I'm going to argue the same thing, that the electric field is constant over any Gaussian surface. The amount of charge is inside the Gaussian surface. That blue shell is not within there, and it won't change any of my calculations. And likewise, from the physics, I will answer it the same way I just did for inside the ball, that what total electric field do you get from the charges that are in the shell cancel off. Anytime you're in this ball, you can go anywhere in here, draw 2 lines, look at top and bottom, look at left and right. Top and bottom, like I said, I think are easy to see, they cancel off. Left and right's not so easy, but I'm telling you, less charge, close distance, more charge, bigger distance. Since the bigger distance, the area increases as r squared, but the field gets weaker as 1 over r squared, they cancel off. And so you get exactly the same equation. So don't kill yourself over this problem. This problem could have been long. And I doubt if I'm going to do it in 10 minutes. But if I had to do all that over again, it would take it much longer once I realize that I don't have to do volumes 1 and 2 again.
I have a question. Like for first one, is that A smaller than R?
That is for R. These are for positions that are smaller than the radius of the ball.
Picture is longer.
Oh, now, okay, let me make it very clear. They have shown a Gaussian surface in area number 2. What I need to do is a Gaussian surface in 1, 2, 3, and 4. So, I don't want to write on the screen, but imagine a Gaussian surface in here. That's what I'm doing first. Because I have to do a Gaussian surface for every position. Inside, volume 1. Volume 2 is the one they show. So this would be a Gaussian surface for volume number 2. 3 is going to be a little bit harder, so why don't I jump to 4 real quick? What am I going to get for 4? Volume 4. R greater than, C. What am I going to get for the electric field? And if I draw a Gaussian surface way on the outside, see how the charges are spherically symmetric? See how I would say that they have the same value everywhere on the Gaussian surface? They'd be radially outward. I would do the same calculations I would, but now I need to include all of the charge that is inside the Gaussian surface. And now doesn't that include the blue shell as well as the ball? So let's add them together. What is the charge total? Yeah, and so this would be a negative Q R squared. And so again, it would look just like a ball where the total charge is now a negative Q. So the electric field would be radially inward. The harder one and the last one is volume number 3, where we are looking at values that are greater than B, than less than C. And if we did all that, we would go through and end up with how quickly do I want to do this? Well, the total charge that's inside the Gaussian surface. And so if you imagine a Gaussian surface, Wrapping around volume 3, how much charge is in there? Well, there's Q from the brown ball for sure. Then there is minus, and it wouldn't be quite 2Q, right? How much would it be minus? Well, it would be a fraction of 2Q, wouldn't it? What fraction? Well, the fraction of how much volume you have compared to the whole volume of the shell, right? So if I only go a little distance, the whole volume would be 4/3 pi r cubed minus b cubed. The whole volume would be 4/3 pi c cubed minus b cubed. And so there would be my charge inside. And fortunately, a lot of things simplify, and it can look a lot better than that, but we're out of time there. But that would certainly be an advanced problem. What is the electric field? Everywhere.